Hello, in the last lecture we discussed about the modes and did spoken about that along with this longitudinal or axial modes, the laser output is characterized basically by the TEM or transverse electromagnetic modes. So in which we are seeing total three types. One is TEM00, TEM01 and TEM11. Now, we also mentioned what is this TEMMN stands for, okay, how they are integers or what do they represent, okay. Now, in today's lecture, we will see what is called as the Gaussian beam. Gaussian beam. So, when you say Gaussian beam and how it relates to TEM, that's very interesting. Now, when I explained last time that this transverse electromagnetic TEM00 is itself is called as the Gaussian beam, correct? So, which means what? This is the lowest electromagnetic mode structure, because I said the word TEM00. Fine. Now, this is what basically the purest laser beam possible, okay, and it is characterized by the lowest divergence of any mode, which is limited only by diffraction. Okay, this is the typical graph of the Gaussian beam or TEM00. Now, this beam is basically characterized in intensity. So this is my intensity axis. Intensity in both axes given by the expression I of y is equal to I0 e to the power minus 2y square by w square. Now what is I0 over here? I0 is the maximum intensity of the beam. Okay. And what is my y? This I of y is the distance from the center of the beam. Fine, distance from the center of the beam, and w is basically the radius of the beam, which is also called as the spot size. Very important word. W is radius of the beam, and it is also called as spot size, the middle part. Okay. Now this radius of the beam, the w, expands as we move away from the laser, and therefore the calculation of intensity applies to a cross section of the beam at an arbitrary distance away from the laser. Okay. So now inside a cavity consisting, okay, we can see this diagram now. Inside a cavity consisting of two concave mirrors with radius of curvature equal to exactly the distance between them. Okay, that's the reason I use this paper again. When I taught you cavity configuration, there we have seen total 4 types. One is plane parallel resonator. Here we had 2 plane mirrors. Okay. In second one, which was confocal resonator, where we had these 2 concave mirrors and L is equal to R, which means distance between the 2 mirrors L, it was same as the radius of curvature. Fine. And in the hemispherical resonator, we had seen this diagram, and long radius resonator, this was a diagram. So this we are trying to use it. Okay. So inside a cavity consisting of 2 concave mirrors with radius of curvature equal to exactly the distance between them. So L is equal to R. Fine. Which is symmetric confocal resonator. So this is my confocal resonator. I use the word symmetric because same distance we have kept it. L is equal to R. This diagram is basically Gaussian beam inside a laser cavity, which I am talking now. So in this beam converges at the center of the gain medium, which is called as the beam waist or W0. Now this is what basically, this is the smallest spot size, what I mentioned earlier, the spot size or W, okay, smallest spot size of the beam, and the width of the laser beam at this point is governed basically by the wavelength and separation of the cavity mirrors. What is the separation of the cavity mirrors? Which is L. So I can draw it here. From here till here, the distance is capital L. Okay. So what is the formula for this W? I write over here. The formula for this W0 or the beam waist is given by lambda, which is the wavelength, into L, distance between the two mirrors, divided by 2 pi raised to half. Right? Now, the volume of the amplifier utilized in the laser process is not the entire volume of the gain medium. A Gaussian beam in a laser cavity, this one in a laser cavity, does not utilize the entire lasing volume and will not give the highest output power for a given laser. Okay, so who does that? So the higher order modes can utilize the gain medium. Now higher order modes means what? As I mentioned earlier, TEM00 is the lowest mode. But other than that, we have TEM01, okay, or TEM11. So these higher modes can utilize the gain medium more effectively than the Gaussian beam can. Okay. So now inside this cavity, the wavefronts of the Gaussian beam, okay, do not stay constant but deviate, okay, but deviate, and at the beam waist, at the center, okay, wavefronts are plane. That's what this diagram says. Wavefronts are plane, but as they move forward, the cavity mirrors, the shape changes. So I can either draw it like this also, little curved, as they reach towards the mirrors. Okay, to why it happens? To match that of the radius of curvature of the mirror. Okay, so essentially of a spherical wave. So wavefronts existing, the wavefront exiting, okay, exiting the laser through the output output coupler also have this characteristic shape, and exiting through the diverge at an angle which is given by the formula given by theta is equal to lambda divided by pi omega 0. Okay, so what is theta over here? Given theta is the half angle of divergence. Okay, now this formula is derived from radial expression of radial expression for a Gaussian beam, which is basically complex in nature. Okay, so this is all about what they mean by Gaussian beam and the few characteristic of the Gaussian beam, how it behaves, does it utilize the full laser cavity volume, and so on, or what is the formula for beam waist, okay, how much is the maximum intensity, and so on. Okay, now the next topic which we will study is again very interesting and important, which is called as the resonator stability. Okay, so to study that, resonator stability, so this will be able to, in this topic we will study even G parameters and the problems also. Right? Now moment I say what do you mean by the resonator stability, okay, I can again look at this figure. So what happens basically, the general form of a laser cavity is with these two concave mirrors with coincident foci in the center of the laser medium, okay, as given in this diagram. So in this arrangement, or in the confocal arrangement, a true Gaussian beam travels or transfers between the concave mirrors, and it can be found in which the curvature of the wavefront of the intracavity beam approaching the mirrors matches the curvature of the cavity mirrors. Okay, so because of this, what happens? This ensures that the beam reflects perfectly back on itself and is completely trapped within the cavity, which defines basically the stability which we want to study now. So this is the job, or how it travels or get trapped within this cavity. This is basically defined as the stability. So any ray within the cavity can retrace itself exactly after one round trip. Okay, going from here, again coming and hitting back. Okay, so that way we are going to count the one round trip through this cavity. So if one mirror is partially transmitting, the beam that passes through the mirror, which becomes the output beam, continues to diverge. Okay, so in stable resonator configuration, okay, what happens? The light between these two mirrors is trapped completely, and the beam is reflected back on itself within the cavity, keeping the power density large to encourage the stimulated emission. Okay, so to determine stability, what do you mean? To determine stability, we introduce resonator G parameters. Okay, so what is the formula? So one representing each mirror. As we have two mirrors, so we'll say there are two parameters given by G1 for the first mirror and G2 for the second mirror. Okay, so how do they define? Which define the beam path relative to the entire cavity. Okay, so basically G parameter is given by 1 minus L by R. Okay, now what is this L? L is the length between the cavity mirrors, which I showed you here also. From here till here, this is my capital L. Fine. Okay, and what is R? R is the radius of curvature. Okay, radius of curvature. Now when I say that I have two parameters, G1 and G2, so how will my G1 will be given by 1 minus L by R1, and G2 will be given by 1 minus L by R2. And what is the condition? Stability is defined by the condition. What is the condition? That the value of G1, G2. So I'll write it over here. So this is 1. So this is less than or equal to, less than or equal to. So this is very, very important condition. Whatever value, the product of these two parameters should always lies between 0 and 1. It should not be ever be greater than 1 or lesser than 0. That's the condition to check the stability. Okay, now to understand this, okay, I'll just show you one diagram. Now what is this diagram basically? Okay, this is the diagram for the parameters for resonator stability. So here I showed again these two mirrors, concave mirrors. Distance between this mirror and this mirror is L. Okay, and exactly R1 is for this mirror, R2 is for this mirror. Okay, this is the basic understanding. That's why I made this diagram, to get this clearly. This and this is same, but here this is much more for the specifically for the stability is concerned. Okay, now as I mentioned, to understand this condition, what is this value G1, G2 lies between 0 and 1 means what? Okay, now to do that, suppose you have been given the laser cavity between these two concave mirror, or you say spherical mirrors. Okay, and distance between them, suppose they say L is 1 meter. Okay, and each mirror, both this R1 and R2 equal to, it's given to be 60 centimeter. So radius of curvature. So what do you have to check now? You have to check, is it stable or unstable? So what is the formula for G1? As I told you, G1 is 1 minus L divided by R1. And what is G2? G2 is 1 minus L divided by R2. Now to get this G1, L is 1 meter, fine, and R1 is how much? 60 centimeter, which means 0.6 meters. Okay, so if you simplify this, how much do you get the value? You get it around 1 minus 1.67. So this gives you minus 0.67. Same will be valid here also. Here also I have to write 1 minus 1 upon 0.6. So this is also minus 0.67. So when I have to multiply them together, what will I have to do? Minus 0.67 into minus 0.67 gives you plus, okay, and the value will be 0.4489. Okay, what is the condition? G1, G2 should be less than or equal to 1. So this value is exactly in between 0 and 1. So we can say 0.4489 less than or equal to 1. So we can say this is stable. Okay, this is the way we can solve the simple problem. Now in second problem, again the L is 1, suppose 1 meter, and the value of radius of curvature R1 and R2 is given out to be 0.45 meters. Okay, this one R1 and this is R2. Same way we can find out. So how much is G1? 1 minus 1 upon 0.45. Okay, same way even this is G2 also. So this will give me 1 minus 2.22. Okay, so this will give me minus 1.22. Okay, G2 will be also same. So I can say therefore G1 into G2 is minus 1.22 into minus 1.22. Okay, so if you multiply them, we'll get definitely plus, and the value will be 1.4884, or I can say 1.49 approximately. Okay, and this value is higher, so we can say very confidently that the resonator cavity will be unstable. So this is the way we can make use of these G parameters to check the given resonator cavity, is it stable or not stable. So here we have seen it is stable, and in this case it was unstable. So this is the diagram to show the parameters for the resonator stability. Okay, so this finishes, I think, 100% our module 2. Okay, now for the application sake, for the last module, I think I will give you few notes and work little more on the MCQ, which will help you for the final examination. Okay, so 3 modules, theory part is 100% done. Applications, you can read any book. Okay, I'll give you few notes in short and try to work little more on the MCQ part. Okay, go through it. Any difficulty, feel free to ask. Thank you very much.